I will be assuming some familiarity with Matroid theory. So if you have any questions, please let me know. But even if you don't know everything there is, but matroids, hopefully some of the similar terminology to other concepts will at least give you an idea of some of the things I might be talking about. And this is going to be a brief introduction to matroid orientability, especially with regards to real representability. So real representability is one of the sort of oldest and most fundamental problems in matroid theory. If you remember what I last talked about in the seminar, it's difficult. It's difficult in many sort of different perspectives, whether you're looking at sort of an axiomatic approach, excluding minors, or sort of a complexity theoretic perspective. So how orientable matroids were originally introduced to me was with the hope that maybe orientability could be a tool to better understand sort of real representable matroids. So it stems from this observation that all real representable matroids are orientable. And if you're orientable in binary, then you need to be real representable. And if you're orientable in ternary, you also have to be real representable. So maybe if you have this additional condition of being representable for some field and you have an orientation, then this forces real representability. Unfortunately, this is false. And sort of for many of the sort of finite fields, it's known that you have a matroid representable over that field that's orientable but is not real representable. Although it's unknown whether like GF4 representable and orientable implies real representable. That was sort of the next step. Okay, so still have to define an orientation of matroids. So one of the ways to axiomatize matroids is with circuits. And these come from sort of thinking about cycles in a graph. And if you look at cycles in a graph, the first sort of three immediate observations you might make is that, well, no cycle, it doesn't contain any edges. You can't have, if you have a cycle, you can't have a smaller cycle contained within it. And the last one is circuit elimination for matroids. If you have sort of two cycles in a graph with a common edge, you can eliminate this edge. So I realized I've used E both in my example and as a generic element. In this case, the only, yeah. Yes, this is true for, yeah. So I can eliminate, I can eliminate the element E from the cycle CDE and the cycle ABDE, for example. So what if I look at a digraph? So I'm going to add a direction to all of the edges of my graph. Now if I look at cycles, there's a natural bipartition of the edges of a cycle. If I just traverse a cycle in a specific direction, so here I've just used clockwise because it's planar, I can either have an edge with this cycle or sort of against it. And I can bipartition each of my cycles using whether an edge follows or goes against sort of this block. And now, if we're to look at circuit elimination again, you can observe that these bipartitions have to respect a specific property of eliminating sort of a common edge. Specifically, when I'm eliminating a common element, it has to be eliminated from both sides of sort of the bipartition. So considering the cycles A, B, C and the cycle C, D, E, if I'm eliminating C to get sort of, so the first two cycles in this list to get the third, I'm eliminating C from both sides of sort of bipartition. And this is sort of the additional property I need to get from sort of matroid to be an orientable matroid. And I've said that all real representable matroids are orientable. So now, I'm not going to completely prove, but I'm going to at least see why this is true. So here is a real representable matroid. Its vectors are sort of encoded in this matrix. And on the left, I have sort of the affine representation of these elements. So a circuit in this matroid corresponds to a linear dependency of these vectors. And if I'm over the reals, I can get sort of a very natural bipartition is just look at the signs. So the sign of each linear dependency will give me a bipartition. And now, considering sort of circuit elimination, one can sort of check that it follows if you just do an immediate sort of linear sort of elimination, you might still need to find sort of a minimal circuit, but you can check that this property is satisfied. So this is sort of a linear algebraic interpretation of what these bipartitions encode. Since we also sort of have an affine representation of this real representable matroid, we can also think of sort of what these bipartitions look like here. So now, when you have a linear dependency, you have this bipartition with respect to different signs, and a common sign can be used to be sort of a convex hull in the affine representation. So having a linear dependency like this means that the affine hull of both sides, or sorry, the convex hull of both sides sort of in this affine representation, they have to intersect. So there's some combination of A and B that will be common with D and E in this case. You can check that for sort of any of the circuits I have here. So this is a possible orientation of this matroid. I could multiply sort of the last column E by -1, and in this way I can sort of reorient, and this will give me sort of a different orientation, so just changing the direction of an edge in the graph.
What does the negative sign mean? So how do you interpret this as the orientation of the matrix?
The signs. So for, here, I should do it. So for positive, negative, negative, so I'm really just looking at the signs. So I'm just using the signs of each element in each linear dependency to get this bipartition. Yeah, so if you have, considering the first two cycles, for example, if I want to eliminate C from them, I can do sort of just linear elimination to get rid of C. So I just add these two sort of linear equations together. And I guess in this case, I'll get something contained in A, B, E, D will be sort of the resulting combination. Yeah. So it's the additional constraint on circuit elimination comes if you just follow the signs of linear dependencies. Yeah. And when I've multiplied the last column by -1, all I've done is just change the sign in all of these linear dependencies. So I've just changed the position of E in each of these bipartitions. Right. Yeah. So this is the sort of orientation of the circuits. If we look at the sort of dual matroid, so the matroid whose matrix is whose matrix has a row space that's the orthogonal of the row space of the original matrix. We can also sort of consider the co-circuits. So a co-circuit in a matroid is a complement of a hyperplane. And I can do the same sort of thing as before, consider the signs in each linear dependency and bipartition each of my co-circuits with regards to these signs. And this also sort of has a nice geometric interpretation. So if I consider a circuit of my dual matroid, this is a minimal dependency, so it's going to be a minimal non-zero vector in the row space of my original matrix. This is the complement, the support is the complement of a hyperplane of my matroid. And looking at sort of the signs, they're how the elements in the affine representation fall on either side of this hyperplane. So bipartition of co-circuits in the sort of affine representation are how each hyperplane actually divides the elements up. Yeah, so this is also a description sort of its affine representation. And in fact, not only are sort of the underlying matroids dual, but we also have duality for oriented matroids. So for regular matroids, for non-oriented matroids, duality is normally given by looking at bases or the rank axioms. You can also define duality by looking at circuits and co-circuits and using orthogonality. And this is what we'll do for oriented matroids. So this is not, this is going to look like an arbitrary condition where if I have two bipartitions of ground set, I'll say they're orthogonal when both of these are either empty or non-empty. Sort of most illustrative with a non-example. So if I think of signs again and have a bipartition that sort of corresponds to sort of the first vector, the signs of the first vector, and have another bipartition that corresponds to the signs of the second vector. If one of these is empty and the other is non-empty, that means they have the same sign on their common intersections. So this is sort of all orthogonality means. In the oriented case, I just never have the same signs on their common support. Sorry? So x1 is, say, all the positive in the first vector, and x2 is all the negative entries, and the 0 entries aren't. Yeah. So here, x and y are the support of these vectors, and x1 is the positive entries, x2 is negative, for instance, up to sort of sign. And y is the same for the other vector. And if they sort of only have the same sign on their common support, then they're not orthogonal. So that's what orthogonality means. So yeah, yeah. So the first set equation here I have is where sort of if x1 and y1 correspond to positive, I'm looking at whether they're both positive and they're both negative. So where sort of the sign is the same. And the second is where the sign is different for each of them. So I can't have all their signs be the same or all their signs be different, is all that these two set equations say. Oh, I don't care what they are. They're plus or minus r. So there's or 0, right? I only care about their intersection, or the area where they both have non-zero entries.
So almost everything will be orthogonal. Like if there's some large overlap, then only not orthogonal if it's exactly matches or it's exactly opposite.
Yes. Yes, exactly. And yeah, phrasing it like that, that seems like a, non-orthogonality is a bit of a, rarity. But this is enough to precisely give uniquely an orientation. Yeah, I mean, for matroids, it's also sort of remarkable that orthogonality is really that the intersection of two things isn't one. And that's enough for for matroids. This is enough for oriented matroids. Yeah. So if I have an orientation of matroid, I have a unique bipartition of the co-circuits, and in fact I could have discovered the co-circuits with sort of minimal orthogonality set. So I have a unique bipartition of each co-circuit that makes so that every co-circuit, sort of signed co-circuit, is orthogonal to every signed circuit. Oh, I just mean the two different parts of C. I'm using superscript to denote parts of a bipartition of the variable.
It's an unordered.
It's unordered, yeah. Often how You can also consider oriented matroids where they're ordered, but if you have one, you also have the other. That's often where it's also presented. But sorry, they can be empty, yeah, but they can't both be empty. But yes, one or the other could be empty. And the reason for this, sort of the very important lemma here, is sort of the following. If you have a matroid and you have a co-circuit of this matroid and two elements in this co-circuit, you can find a circuit that intersects on exactly these two elements. And if you sort of down, you can sort of see why. If you have a co-circuit, so the complement of a hyperplane, which means you can find an independent set that is one short of a basis of the matroid. And if you add E or F to this, you will get a basis. But if you add both, you're going to be 1 over the size of a basis. So this independent set, union E and F, must contain a circuit that contains both E and F. So yeah, think of these complements of a hyperplane, and if you think of it sort of geometrically, you can see why this should be true. Yeah, in fact, like, yeah, that's probably an easier way to. And this is how, it's weird. For some reason, I chose to do a geometric explanation for that, but I'm going to do a graphical explanation for how you actually use this. Yeah, so if I have a planar graph, then I have a dual graph, and if I have an orientation of sort of this underlying graph, I'll start by just arbitrarily choosing an edge or an element of the dual and considering sort of oriented. Now I'll use, so orthogonality for the graph case is essentially that you need, if you have a bond and a cycle that intersect on sort of two elements, they can't sort of both be in the same sort of direction. And with the dilemma, you can sort of consider any other edge as long as you have sort of connectivity, and orthogonality will tell you sort of how this edge is oriented. And you can do this as long as you have connectivity for sort of all edges in a dual graph. And this is how you can find an orientation of the dual graph. And the same type of thing works for orienting a matroid, where you consider sort of each cycle individually, and you can figure out which side of the bipartition each element should be. And then you can check that this is sort of a consistent orientation, and that sort of the underlying matroid is indeed sort of the dual matroid. But yeah, it's sort of the same kind of idea where, you do it with respect to a given element in the bipartition. Okay. So another, so oriented matroids are closed under duality. They're also closed under minors. You can, deleting, you just get rid of the elements, and contraction, you could dual, delete, and then dual. And you can also think about what sort of an exercise, how the orientation would look like. Another operation that oriented matroids are closed under is relaxation. So for matroids, if you have a circuit hyperplane, so which means you have a circuit and a co-circuit that are disjoint but who union to the whole ground set, then you can relax the circuit hyperplane by sort of breaking this dependency, this circuit, and this is the only thing you change. So geometrically, you can think of it as just perturbing the elements in the circuit hyperplane, and these are the only, this is the only sort of geometric relation that you change within this matroid.
I didn't quite understand what the new matroid is after the operation.
So if I have, this matroid has circuit C, then the new matroid will have circuits where I've gotten rid of H, but H was a circuit hyperplane, so it had the size of a basis, so H with any other element is going to be a dependency. So I've gotten rid of this circuit, and I've added new circuits that consist of H and any other element. So yeah, I've sort of just broken only this.
Same as the circuit I made relaxation in matroid.
Oh, sorry. Yeah, this is circuit hyperplane relaxation in matroids. I'm building up to how you can sort of use the same intuition to figure out how orientations behave. But yes.
So it's a circuit that's a complement of a co-circuit?
Yes, this is a circuit that's a complement of a co-circuit. So the complement of a co-circuit, thinking of like bonds and graphs, for example, is a hyperplane. So yes, this turns H into a basis of the matroid, and it being a basis of the matroid means it's actually like a free basis. So if you think of the fundamental graph, the fundamental graph with respect to a free basis is a complete graph.
Right, and just because this by definition does the same thing as you?
Yes, exactly. Yeah, it does. Originally, I actually described what happens to the co-circuit. I mean, yeah, just replace circuits with co-circuits and you get the same, yeah. But the site was getting crowded. So but yes, it is exactly the same operation to do. So this is, yeah, it's a cool operation and comes up a lot and it's sort of useful. And you'll see how you can use it later on in this talk. So now I'm going to use sort of the geometric intuition, but now considering sort of the observations I made about circuits and co-circuits. So if H has this bipartition such that the convex hull of both parts have sort of common intersection point, and this hyperplane sort of splits all the elements into these two sides, what I'm going to do is just think of what happens if I sort of infinitesimally move H1 up and H2 down. So I don't want to change any other dependencies or any other sort of geometric structure besides thinking about what happens if I sort of do this. And this is certainly a bit more complicated, but if you do this and look at the circuits, you've gotten rid of this circuit again. But now any other dependency is either going to be sort of H1 and H2. So H1 and H2 if E comes from the side of G1, or E is going to be with H1 if E comes from G2. And remember that these bipartitions are such that sort of in affine representation, they'd have convex hull. And you can check that H1 will have sort of an intersection with H2 union an element from G1. So because H2 is down here, an element of G1 is up here, the convex hulls should pass through H1. If this affine representation actually sort of was a thing, and yeah, this is sort of what's happening. The common intersection point of these two circuits has moved, slightly up into H1 in this case, and slightly down into H2 in this case. So yeah, H1 would intersect H2 and anything in here. Or the convex hull of that. Yeah. But the point is, this preserves orientability. You still have some, well, not sort of necessarily an affine representation anymore. You have the orientation sense of this geometry. Yeah. G is the complement. Yeah, it's yes, exactly. It's a ground set minus H. It's a cosine. Yeah. Yes. If you have real representation, you can figure it out. If you have an orientation, yes, it would be determined.
The orientation, sure.
Yes, exactly.
But when you pick, because you've got these unordered lists H1, H2, G1, G2. So when you select H1 from that list,
yeah.
G1.
No, I moved H1 up and H2 down. Yes, exactly. Yeah, and up to, I could reorient. So I think the appropriate reorientation would be essentially change the signs of everything in G. I think that's what it would be, just to change these bipartitions that you're observing. This asymmetry, yeah.
I was just trying to think of like what this means if we don't have a representation of it. Because then you just have got the equation.
Yes, then you just have the equation. I mean, and very much so, this doesn't necessarily keep representation, but this is how you can think of it to figure out what orientation should be. But I'm about to show you can use this dramatically to make things that don't have any real representation. And it's going to sort of make this gap between oriented matroids and real representability. So sorry, if yeah. So orthogonality, as Kevin was pointing out, this is the same thing in the dual. You can also, to figure out the co-circuits, you can also just do the same thing here. And that would, so in that case, you're thinking of how do the new hyperplanes split up these points, and the new hyperplanes will look like H minus an element of H. So if you think of removing an element from H1, it should go onto the same side as G1, right? So if I take, if I've removed this element, these three would form sort of a hyperplane, and H1 would go onto sort of this side, right? And that's And yeah, and that's sort of the observation you can think of how the hyperplanes would split, or the co-circuits would be oriented. But while this does preserve, yeah, does that, yeah? Okay. Sorry, maybe you misunderstood your question. Oh, yeah. Okay. Yeah. So while this preserves orientability, it does not preserve sort of representability. So this, what I've drawn here, is currently a real representable matroid. I've just taken sort of 3 lines that are coincident. Excuse me. So the union of any 2 of them is sort of a circuit hyperplane. And in particular, I'm going to look at sort of A and B forming a circuit hyperplane, and I'm going to relax it. So it is no longer going to be sort of a circuit hyperplane. But the union of any other 2 will be a circuit. So if you were to sort of think of an affine representation or a representation over sort of any field, the fact that A, B, C, any pair of 2 form a cycle, and all 3 of them are sort of rank 3, forces A, B, C to be coincident. So in any representation, they should have an intersection of these 3 points. And the same argument works if I look at B, C, and D. They should be coincident lines in sort of any representation. So A should contain the intersection of the lines given by B and C, and D should contain the intersection of these 2 lines as well. But just by, transitivity, this point should also be contained in A and D, which means that A and D together should be a circuit, but we forced it not to be. So this matroid is not representable over sort of any field, and it certainly doesn't have an affine representation. And even if you think of just perturbing hyperplanes or sort of structure here, you can just think of how curves would, as long as they're sort of well-behaved surfaces in any space, this intersection property sort of prevents this from having a geometric interpretation in the reals. Okay. So one might hope that if you get rid of sort of this non-representability, orientable and representable might tell you that you do have a real representation. This is also not the case, but to construct counterexamples for this, I'm going to need it to be representable over some field. And the way we're going to do this is we're going to start off with something that is, again, sort of real representable, and we're going to destroy circuit hyperplanes to get something that is not real representable, but is representable over a different field. And the way we're going to sort of be able to be representable over a different field, but not the reals, is by using a property of GFQ that is not satisfied in the reals. Specifically, having an element of a certain order. So to build this example. The sort of structure we're going to be using is swirl-like matroids. Important sort of observation is, if you remember from my previous talk, I discussed these as well. Important sort of observation is the determinant of this matrix is 0 precisely when sort of these alphas multiply to 1. So a swirl-like matroid will have sort of a cyclically ordered basis where all the elements lie sort of in between cyclically consecutive line and span of cyclically consecutive basis elements. In this way, we can sort of think of encoding algebraic conditions. So yeah, we'll have that sort of a transversal like this is dependent precisely when sort of the corresponding values multiply to 1. Yeah. So for an odd prime power, at least strictly greater than 3, we can find an element that has even order. And this is important because the reals do not have any elements of order larger than 2. You only have -1 squared is equal to 1. So you can start off with this swirl-like matroid that uses 1 and -1 on sort of each of these edges. And an even number of -1s will always multiply to 1. So any sort of transversal that uses an even number of -1s will be dependent, but will not be dependent if it uses an odd number of -1s. And each of these transversals you can check as a circuit hyperplane. So we will relax all of them except for sort of the ones I've given here. So this has an even number of alphas in this case. This also has only sort of 2. And this will also sort of have an even number of alphas. So these can actually sort of be found by relaxing circuit hyperplanes, all but these sort of circuit hyperplanes. And what these circuit hyperplanes do for us is this one ensures that we do have these sort of labelings of 1s. This will give us that sort of the corresponding elements are each sort of the same. They are the same alpha. And this one finally tells us that sort of alpha to the 2k is 1. So we've done a whole bunch of relaxations from something that had an orientation. So this will still have an orientation. But because this algebraic condition is only satisfied over G of Q, but not the reals, this is G of Q representable, but not real representable. Yeah, so this should be somewhat familiar if you've seen the previous talk. And like this type of idea of using relaxations can be used for sort of even powers where 1s is composite in sort of a different fashion. And we can sort of build upon this to just make real representability seemingly just as bad as we had before. So orientability does not seem to help sort of in any of these fashions, just because we have relaxations that sort of break this idea of representability. Yeah, so these again just are with regards to an axiomatic over sort of logical language, if you look at X2 minors, or just complexity theoretic perspective. So this does seem to form a bit of a gap between orientability and real representability. Doing relaxations has seemed to let us go wild with regards to structure. And it seems in some sense, that maybe it's because we're thinking of these representations sort of, or these real representable matrices in the wrong way. Like, why are we interested in oriented matrices still? And instead of thinking of affine representations, so instead of looking at the vectors, each of these vectors, and scaling so that they lie in a common hyperplane, I don't want to say dual because that means something for matroids, but think of the adjoint where instead of each of these vectors, I look at the corresponding hyperplane that each of these vectors is normal to. I didn't want it to get too messy, so I've only drawn sort of the first three here, A, B, and C. So these each sort of give a hyperplane and a sort of signed direction. I have the positive and negative side. And now, if these all pass through the origin, so if I take some hyperplane that does not pass through the origin, I can capture sort of, and that sort of, as long as I sort of freely place this, I can sort of capture this geometric structure. So sort of as I've done here. I've taken hyperplane, and I've now drawn sort of all of the hyperplanes, or the intersections of these hyperplanes with this surface. And so ABC, ABC form sort of this triangle, which would sort of be the interior triangle that would be formed between these. Yeah. Right. So this drawing has sort of some geometric structure associated with this matroid. And what is this precisely? Well, let's consider an intersection point of two of these lines. So B and D. So this will be, you can think of the sort of vector in R3, and this an intersection point will be, again, sort of, will be a minimally, a minimal non-zero vector, a non-zero vector with minimal support. So, yeah, I'm now looking at sort of in R3 the span of this vector. So with respect to each of these hyperplanes, these are the signs I get. So I have gotten a bipartition of everything besides B and D. And I've gotten this bipartition with signs again. And if you recall, minimal elements sort of this row space are co-circuits of the matroid. So each of these intersection points actually corresponds to a co-circuit of the matroid, where the bipartition sort of respects these directions I've given to each of these lines. So this is sort of a more topological drawing of this orientation, where I have intersection points as sort of co-circuits. And you can think what deletion and contraction should have looked like, and sort of nice operations. And relaxation in this setting actually sort of works in sort of a real drawing. All I do is I perturb the line around sort of the intersection point. So I can break co-circuits and by just sort of perturbing it in one or two directions. And this, in fact, remarkably is fully captures sort of any, this type of idea fully captures any sort of orientable or oriented matroid. This topological representation where instead of lines, you have pseudolines. So in projective space, a pseudoflat is going to be the sort of image of sort of canonically embedded sub-projective geometry by sort of a self-homeomorphism. And we'll call the arrangement of pseudo-hyperplanes as sort of a collection of D-1 pseudoflats, where the intersection condition I need is that any subcorrection will have to intersect to a pseudoflat. So I can't have two lines or two pseudolines, for example, intersect in sort of 2 points. Oh, sorry, they can't they cannot intersect in 2 points in the projective projective plane. And more generally, this is the condition that not having two pseudolines intersect that. So every two pseudolines in the projective plane have to intersect in exactly 1 point, and this is sort of the general condition you'd get, extending that. And remarkably, like any oriented matroid up to sort of reorientation is in one-to-one correspondence with sort of a topological equivalence class of arrangements of hyperplanes, of pseudo-hyperplanes, I should say. I do need this essential condition here. And what essential means is that I can't have a common intersection point of all these pseudo-hyperplanes. They have to be, because a common intersection point of all three hyperplanes would sort of, think of projecting it out, it would be, so topologically oriented matroids have this close tie to sort of real space still, even if the affluent one does not seem to. And yeah, thank you.
Thank you. Any questions?
What's the idea of ensuring that there is no polynomial certificate?
So it's of typically, like it's always exponential. So if you go back to my old talk, like it is a lot of the structures behave the same. Actually, so real representability. Which of the two do you mean? I mean, I guess both. But real representability is by having a swirl-like matroid again, where exactly sort of one of many transversals satisfies the condition. So you need to check all of these transversals to ensure that you either have or don't have a transversal that satisfies the condition you need. So so it's something like alpha to the n. It's this type of thing. I think. Oh yeah, I mean, yeah, it gets more complicated when you try and do orientability with it. But it's no, it's sort of that's not it at all. It's alpha's not that, but this. So if it's, I should do 2k. Let's actually do 3k. So you can't have this over the reals, but you can have over other fields. But knowing sort of which is alpha and beta could involve checking like exponentially many sort of things. It's always sort of a highly symmetric structure where you need to check. Yeah. I can. It's probably easier if I draw a picture, but I can do that.
What does a non-orientable, real representable matroid look like?
Oh, there are.
Oh, they're all.
All real representable matroids are orientable.
Right. Oh, but over a finite field, you can have non-orientable matroids.
Yes. So this is, yeah. And to show something is non-orientable, similar how you'd show something is non-sort of representable, you follow through what a representation would look like. And yeah, so orientability, so characterizing orientability itself, I think, is also a very interesting problem. It is also very difficult from a complexity sort of theoretic standpoint and excluded minor standpoint. It's unknown for sort of axiomatic, but I do think that's an interesting problem on its own. But yeah, so checking whether or not matroid is orientable is sort of a difficult problem. Something I did not talk about is there are orientations that don't have what's called a realization. So they're orientations that do not correspond to any real representation. So I think U24, U48 is what I meant. U48 has an orientation that does not correspond to any signing or any, to the signs in any sort of real representation of this. So orientation sort of, oriented matroids are, there's certainly more going on there. Yeah.
Does the problem still have high complexity when you restrict to like binary or ternary matrices?
So restricting to binary, oriented binary, I mentioned it, this is not orientable So because this is going to be an exclusion minor for orientable and binary, and this is how you actually can show that orientable and binary is regular. Because, yeah, to be binary, you have that as an excluded minor, and to be binary and orientable, you have to have both these as an excluded minor, and I guess the non-final as well. But you find that you so it's at the very beginning, and ternary so so orientable and binary does mean you're real-representable. Orientable and ternary is real-representable. I don't think it's so not known for quaternary and orientable. And yeah, this is a problem. It's thought about. That I think is sort of an interesting problem. It's conjectured not to be for sort of good reasons associated to like pastures and hyperfield, more generic senses of. Something I didn't talk about in this talk is you can also consider orientability. Instead of circuits, you can consider an ordering of bases that sort of corresponds to the signs of determinants. So instead of looking at signs of dependencies, I look at signs of determinants of a real representation. And this type of conception of capturing signs also gives a way to axiomatize orientability. But yeah, it's sort of an interesting. Orientability seems very much to be related to signs of fields, but there's lots of weird stuff you can do by either using relaxations or I mean, if you look at the topological pictures of things, you can like see how you might get really weird, but sort of, in some sense, ordered structure.
So one is, so all this, the hardness result is about the deciding whether or not matrix is real representable, right? And for this polynomially certifiable thing, are you assuming that the matrix is given by independent oracle?
Yes,
Yeah.
independent oracle.
So you're not assuming that the complex matrix representation is given as an equal,
No.
right? Another question is, what about deciding whether matroid is orientable? Are there known results?
So the I know the excluded minors are difficult. I believe, so the last three essentially are difficult. The axiomatic is, I mean, I would not believe that orientability is, because you have this sort of very, looking at bipartitions, that's sort of not a, that's more, a relation that you can't seem to quantify in monadic secondary logic. And any tool you might use, the known tools to show something isn't axiomatizable just don't work. So I'm fairly confident, but I couldn't phrase the last three. I guess, probably with circuit, Oracle, and
this circuit hyperrelaxation is good tool for disproving the, I mean, good tool to like screw the algorithm, right? If you have, suppose you have a algorithm to decide the real representable, then you give two kinds of input where one is obtained from the other by circuit hyperrelaxation, and the algorithm has to detect whether or not you have done it. But if you want to have the result like this for orientability, you need a different operation, which almost same, but except one place where you change something, then matroid is no longer orientable. I don't know whether you have such an approach.
Yeah. This was one of the things I was actually debating talking briefly about. Now I wish I'd sort of. I think it's it uses more of the finite, like yeah. I believe it's. I think it's known for complexity theoretic to be difficult, but I don't know offhand the construction. It is in the book, I think, though. So I think it is related to sort of finite field stuff. But yeah.
Other questions? If not, let's thank the speaker.